observed what really happens inside your computer when you type a word, play a game, or click a link? Behind every action is a system carefully designed to process data, store information, and communicate with the outside world. Today, we'll be exploring computer system organization and architecture, one of the most important foundations in IT. Now, before anything else, let's clear up a common misconception. Computer organization and computer architecture are not the same thing. So let's start with the computer organization. What is computer organization? Computer organization is about the hardware side, the physical design of a system. It focuses on things like how many registers a CPU has, how memory is arranged, and how different components interact. Then what about computer architecture? On the other hand, it is a logical side, the system as seen by a programmer. It deals with the instruction set, data types, input-output methods, and memory addressing. Overall, here's the simplest way to put it. Architecture is what the programmer sees, and organization is how the engineer makes it work. Understanding both is essential because without the design or the architecture and the implementation or the organization, computer as we know them would not exist.
So, we're talking about a von Neumann model and system bus. To understand modern computers, we need to go back one of the most influential designs ever created, the von Neumann model. So what is von Neumann model? Von Neumann model is a computer architecture that describes a system where the data and program instructions are stored in the same memory and processed by the central processing unit using a sequential decode or execute cycle. Computer architecture designed and proposed by John von Neumann in 1940s. It laid a foundation for how the most computer works today. This model describes a computer in terms of 5 key components. First, input unit, devices like a keyboard and mice that fed information into the computer. Second, a output unit, devices like a monitor and printer that sends information back to the user. Third, the arithmetic logic unit, or ALU, the part of a CPU that performs. Third, the arithmetic logic unit, or ALU, the part of the CPU that performs. So there's a question: how are these all components talk to each other? That's where the system bus comes in. The system bus is like a computer's main highway, all connecting the parts together. Without the system bus, the computer's parts will be isolated and no more meaningful processing could ever take place.
Let's proceed with the motherboard components and digital circuits. All of this hardware lives on the motherboard, which we can think of as the backbone of the computer. On the motherboard, two critical chips work hand in hand. The NOR bridge, which connects the CPU to high-speed components like memory, and the south bridge, which manages slower input and output devices. Together, they ensure smooth communication across the system. But how does the motherboard actually compute? That comes down to digital circuit built with transistors and logic gates. Transistors, invented in 1947, replace vacuum tubes. They're small, cheap, and generate less heat. Without them, computers today would still be the size of entire rooms. From transistors, we build logic gates, the building blocks of digital decisions like AND or NOT. Combine millions of these gates and you get integrated circuits. Over time, these circuits have scaled up. First, SSI, or Small Scale Integration, had up to 100 gates. Second, the MSI, Medium Scale Integration, had up to 1,000. Third, the LSI, Large Scale Integration, had up to 10,000. Today, the LSI, Very Large Scale Integration, packs millions of even billions of gates on a single chip. This is why your phone today is more powerful than entire supercomputers from decades ago.
Data representation and number systems. Now let's talk about something every programmer must master: data representation. Humans use letters, numbers, and symbols, but computers only understand binary, zeros and ones. To make this work, we use coding systems like ASCII, where each letter or symbol is represented by a 7-bit binary code. For example, the letter A equals 65 in decimal, or 01000001 in binary. EBCIDC, an 8-bit system once used in IBM machines. BCD, or binary coded decimal, where each decimal digit is stored using 4 binary bits. Beyond representation, computers also rely on different number systems. Decimal or base 10, the system we humans use. Binary or base 2, the language of computers. Octal or base n, a shorthand way of grouping binary. Hexadecimal or base 16, widely used in programming because it's compact and easy to read. Now let's go through a quick example using the decimal number 74. In binary, it becomes 1001010. In octal, it's 112. In hexadecimal, it's 4A. Wondering on how we get 1001010 in binary, 112 in octal, and 4A on hexadecimal? Here's the conversion steps. To convert it to binary, we keep dividing by 2 and writing down the remainders. Now if we read the remainders from bottom to top, we get 1001010. That's 74 in binary. For octal, we divide by 8 instead of 2. Reading from bottom to top, we get 112. For hexadecimal, we divide by 16. Since 10 is written as A in hexadecimal, the answer is 4A. So the same number, 74, looks different depending on the number system. With decimals is 74, binary is 1001010, in octal 112, in hexadecimal it's 4A. This is how computers can represent the same value in multiple ways.
So let's wrap this up with the key takeaways. Computer organization is about the hardware design, while computer architecture is about the logical design. The von Neumann model explains how input, output, processing, memory, and control all work together. The system bus with its data, address, and control buses is the highway connecting all components. The motherboard and digital circuits are the backbone powered by transistors and integrated circuits. And finally, the data representation and number system allow computers to understand, process, and communicate information. Understanding this foundation is essential for anyone in IT. They don't just explain how computers work, they prepare us to build, program, and improve the system of the future. If you found this video helpful, don't forget to like, share, subscribe to our channel for more lessons in computing. Thank you for watching.